Hello, calculus friends. Today we are going to go into section 6. So in this video, we are going to be specifically talking about something called the mean value theorem. So please make sure that you have this note sheet handy. Particularly this sheet, because of all the graphs, would be very, very helpful if you actually print it out. This is going to be a little bit more of a challenging activity for you to just put into your notes. So if you haven't printed it out and you have the means to print it out, please stop the video and go do that first, okay? So before we get into exactly what is the mean value theorem, I have 6 questions that are on this worksheet that I would like us to consider just as kind of prep work of getting to this concept of something called the mean value theorem and why we have it in calculus. Okay, so let's do the first one or so together, and then I want you to pause the video and to try a few on your own. Okay, so we have number 1. We've had this function, okay, this cubic function, and it's graphed, and it's saying that there is some value c, okay, in between 3 and 7. So this is an important part of this. So c is in between 3 and 7, and we're saying that there is a tangent line that is parallel to the secant line containing 3f of 3 and 7f of 7. Now this is already a mouthful, right? So together, I just want us to remember what the definition of these terms are that we're seeing. So first and foremost, what's important is that we're looking at the point 3f of 3, and we're looking at 7f of 7. Now remember that a secant line is just a line that connects these 2 points that are on our function f. So the secant line is roughly, whoops, I'm going to undo that line. It's roughly this. Okay. Now, what they're asking us to do is not only draw the secant line, but they also want us to draw the tangent line. And keep in mind that they told us the tangent line is parallel to the secant line. So where can we draw a tangent line in between the interval 3, 7 that is parallel to this one? Okay, so once again, I want a tangent line that is parallel to the secant line in between 3 and 7 so that we're on this interval. Well, we're going to just have to estimate it. We're not going to know exactly, but I want to draw a parallel line that's touching, I don't know, looks maybe somewhere right along here. Okay, so maybe this point approximately around there. Okay, so the question's asking us, if this is now the tangent line, let's get that on there too. Approximately what is the value of c? In other words, what is the value of x in between 3 to 7 where we will have a tangent line parallel to the secant line that's connecting these 2 points? Well, I'm going to estimate this. What do you guys think this x value is? Somewhere, let's see, this is 4, 5, 6. So somewhere in between 5 and 6 looks a little bit closer to 6. So I'm going to say C is approximately maybe like a 5.8. Okay. Now I don't know that for sure, and I don't want to get hung up on that right now. All I'm saying is that C is somewhere in between 5 and 6, a little closer to 6. I wouldn't be upset if you said 5.7 or 5.5, we'd be fine. Okay. All right. So let's see how this question, number 1, differs from number 2. Okay. So in number 2, function f in problem 1. So once again, please realize that we are referring back to this function. Okay. We still have the exact same graph. But now we're going to say there are 2 values, okay, x equals c, between 1 and 7. So look at that. They just changed our interval from 1 to 7, okay, at which the tangent lines are parallel to the corresponding secant line. Okay, so let's just draw that first. Okay, where is the secant line if we're going on the interval of 1 to 7? Well, the point on the curve at 1 looks to be about there. The point on the curve at 7 is about here. So if I'm going to draw my secant line, I want to connect those 2 points to the best that I can. Here's my secant line. Now, what this question is saying is that the function f has two different values where the tangent lines are parallel to the secant line. Okay, it's really important that we're pulling out that the tangent lines are parallel to the secant line. So go ahead and put this down, where would you draw the two tangent lines that would be parallel to the secant line? And kind of want to draw my parallel line here. And I've got to intersect with the graph, so maybe then down here. Because anywhere else, you got to think, if I started drawing secant line or tangent lines at other places, these would not even be close to being parallel to the secant line. Okay, so can't be there, can't be here, okay? So what the question is now asking us is, can you estimate what would these values of C be? Now there's two of them now. So what do we think? Okay, so here's 2, 3, 4, 5, 6. All right, so my first one, I'm thinking it's like right after 2. So it's in between 2 and 3, but pretty close to 2. So maybe I'm going to call that like a 2.2. I'm not going to worry too much, okay? And then as far as the other one goes, well, it's up here. So it's in between 5 and 6. I think it looks a little closer to 6 to me in the way I drew it. So I'm going to say 5.8-ish, okay? Not too worried. All right, now what I would like you all to do, now that we've done 2 of these together, I would like you to take this worksheet and see what you can do with the next 4. Use it as an exploring opportunity of, well, let's keep looking at the secant lines and what happens when we try to make tangent lines that are parallel to the secant line, okay? Try those 4, then come back to me in the video. Okay, so welcome back. I don't have the answers up, but I want to see how far you got, okay? Basically, in the next 4 problems, I drew in the secant line that was given in each problem, okay? So in number 3, if I take a look at it, it's asking us over the interval of 1 to 5. And so from 1 to 5, I'm drawing in my secant line. And then it's asking us to draw in, potentially, or can we draw in the tangent line that would be parallel to the secant line? Well, we're going to run into a problem because the only logical place where we could draw this parallel tangent line would be potentially, I'm not even sure, like what, up here maybe, something like that. But that point is not differentiable. If you start thinking about all of the tangent lines that exist from the right and from the left, okay, none of these little green lines that I'm trying to draw in are going to be parallel to the secant line, okay? Well, all I'm going to say for the moment is that no, okay, there is no tangent line. So the question asks, is there a value of C? So no, because we don't have a tangent line parallel to the secant line, okay? Now we'll explore that more in a little bit, okay? But take a look at 4, which is the exact same function as 3, the exact same graph. But now the interval was changed. So instead of going from 1 to 5, now the interval goes from 1 to 4. And so from 1 to 4, we can definitely draw a secant line in. So is there going to be a C value? Is there a point where we can draw in a parallel tangent line? Well, I'm thinking it's probably like right around here somewhere, this little red line. So maybe the tangent point is around here. Maybe around C is 3. So I just want you to think about this for a second. Why is there a tangent line that exists in number 4, but there is not a tangent line that exists in number 3? They're the exact same graph. They're the same function. What was different about 3 that made it not possible for us to get a tangent line, which keep in mind, A tangent line, which means the derivative, the instantaneous rate of change, we're saying that that slope doesn't exist in number 3, but it does in number 4. I want you to marinate on that thought a little bit, okay? Because then we come to number 5, okay? Now in number 5, they're giving us the interval 5, 8. So be careful, check your secant line. You cannot be drawing your secant line coming from this point down here because that's not f of 5, or sorry, h of 5. H of 5 is up this point. So if we're going to draw a secant line using h of 5, we have to use the point that exists where h of 5 is defined. Okay, so we draw in our secant line, and now I'm looking at this interval going, is there a place that we can draw a parallel tangent line? So if I start drawing parallel tangent lines along here, I can't even draw it here because 5 does not exist in that interval, right? Like this point isn't defined. So any other place that I can do it? No. So again, what we're having is that there is no C value, okay? Because we don't have a tangent line parallel to the secant line. Sorry, my parallel symbol is a little messed up there. We don't have a tangent line parallel to the secant line. Okay, so here we got another no. So right now my no's are 3 and 5. We couldn't draw in the tangent. Okay, but let's consider this last one before we kind of make any final conclusions, okay? So in number 6, I'm looking at the exact same graph as number 5 again. Same function, same picture, only now my interval has changed from 1 to 5, okay? Well, 1 to 5, here's my secant line. Hopefully you already have that. Can you draw a tangent line parallel to the secant line on this interval of 1 to 5? And my answer is yes, probably somewhere right around here maybe. So approximately around C is 3, okay? All right. So let's kind of come back and take a look at this. The problems that we could not get a tangent line parallel to the secant line were 3 and 5. Now I want you to pause before I actually tell you why, right? What was different about 3 and 5 from 1, 2, 4, and 6? What's the main concept here that is preventing us from being able to draw in our tangent lines? Okay. All right. Well, let's look at 3 for a second. The whole idea of drawing in a tangent line means we need the slope, the instantaneous rate of change, right? Or the derivative. So the problem is that they're telling us it's not differentiable at some point on the interval. Now, number 4 also was not differentiable, but they had a different interval, 1 to 4. This problem in number 3, we were looking at the interval 1 to 5. So even though number 3 was continuous, it was not differentiable over the interval. Okay, so I'm going to change the color up. I know there's a lot going on here. So even though this problem, this function was continuous on the interval 1 to 5, it was not differentiable. And they told us that, right? At x is 4. So it's not differentiable over 1 to 5. Because the derivative did not exist at 4, that is why this particular problem fell apart. Okay? By changing the interval in number 4, we now over here had a function that was differentiable and therefore continuous over the interval 1 to 4. Okay? So now let's look at number 5. Compare it to number 6. What's the difference? even though this function, well, maybe we could take the derivative at certain points, okay? Well, it wasn't continuous. So therefore, if something's not continuous, it's not differentiable, right? So our problem in number 5 is that basically we have a function that is not continuous at a point in the interval. So if they're asking us to look over the interval of 5 to 8, and then we're including this point at 5 to draw our secant line, we have a problem. So if it's not continuous at x is 5, we can't assume or come up with the tangent line being parallel to the secant line. Okay, I can't draw in a tangent line through a point that does not technically exist. Not happening. Okay, so what happened that changed it in number 6 is we changed the interval. So by changing the interval of 1 to 5, well, now over the interval 1 to 5, we have a continuous function. Okay, and it's also differentiable. Okay, so what's going on? Let's kind of take a look at this exploratory activity. In order for us to be able to have a tangent line parallel to a secant line over a given interval, the function has to be continuous and differentiable, or we could just say differentiable over the interval, and that also covers the continuity or the continuous part. Okay, so let's think about what this means a little bit more. What if I came back to problem number 1, for instance, which is definitely continuous over the interval 3 to 7, and it is also differentiable over the interval 3 to 7, which is why we could have a secant line and then find a tangent line that is parallel to it. Okay. What if I asked you right now to find the slope of the tangent line? Could you do that? So basically, I'm asking you to find the slope of the tangent line, which, let's keep this straight then. That means I'm asking you for the derivative at 5.8. Okay. Now it's at 5.8 because that's what we're estimating the C value, right? Like, where do we expect that to be? What is the slope of this line? Whoops, sorry about that, moving the screen. Okay, well, at that point, don't we have enough information to figure that out? Okay, so now I'm adding on to this. This question wasn't on the page already. Well, this line has to be parallel to the secant line. Do you have 2 points on the secant line? Right? Doesn't f prime of 5.8, okay, or the derivative of the function at 5.8, shouldn't that need to be the same then as f of 7 minus f of 3 all over 7 minus 3? Okay, so don't get sidetracked by this. This right here is the slope of the secant line. Okay, the slope of the secant line is the same, it's parallel to the derivative or the slope of the tangent line. So let's just estimate it. That's going to be the best bet that we can do. Okay, f of 7, I estimated that at like 4.2. F of 3, which is this point right here, I just estimated, I was trying to go with some nice numbers, 2.2 all over 4. So that's 2 over 4, 1/2. You just found the slope of the tangent line. And the slope of the tangent line is equivalent to the derivative of f at 5.8. So overall, the slope of this is roughly 1/2. Okay? So ladies and gentlemen, peoples in general, right? What you just did was the mean value theorem, okay? So let's go to our next page and let's figure out like, what do you mean by I just did the mean value theorem, okay? So the mean value theorem says that the average rate of change of the slope of the secant line, okay, so I was using purple on all my secant lines on the front page, okay? So the slope of the secant line over an interval is equal to the instantaneous rate of change or the slope of the tangent line at a certain point, okay? Now, main thing that I'm gonna highlight here for you guys, this is super important. F has to be continuous and differentiable on the interval that we're working with, okay? If that happens, then what this is saying is what we just calculated, that the tangent or the slope of the tangent line, also known as the derivative at that point, is equivalent to the slope of the secant line, okay? The mean value theorem does not tell you what the value of C is, okay? It doesn't even tell you how many exist, but overall, we can end up calculating where that point is, okay? So let's take a look at example 1. So they're asking us to apply the mean value theorem to the function f of x equals blah, 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 over the interval -1 to 1. So first of all, it's saying make sure that the hypothesis is true. Well, what do they mean by that? We need to make sure that f of x needs to be continuous and differentiable. If those two conditions are not met, then we cannot technically apply the mean value theorem, okay? So I'm gonna just calculate this or multiply it out in general because it's gonna be easier when I need to take the derivative. If I'm looking at f of x being an x cubed function, we have a polynomial. A polynomial is continuous over all real numbers, so we definitely don't have any issues over the interval -1 to 1. And we can take the derivative at any point because a polynomial in x third is smooth and continuous, right? There's no sharp turns, there's no gaps, anything like that. Okay, so what this now tells us is that I have some x cubed function and the secant line is going through the point -1 something and 1 comma something, okay? So the first thing I'm going to actually do is I'm going to calculate the 2 points that our secant line is going to go through. So consider the secant line for a second, okay? We know it's going to pass through -1 comma something and 1 comma something, okay? So we need to actually plug in -1 and 1 and find out what those values are. If I plug -1 into this equation, I'm going to end up with -1 minus 1 plus 2. So I'm getting a 0, okay? Then I'm going to plug 1 in and I'm going to get 1 minus 2. So I'm going to get a -2, okay? So I've got my 2 ordered pairs. And what I'm able to do with that is calculate the slope of the secant line. So therefore now, slope of secant line, right, is going to be -2 minus 0 over 1 minus -1, -2 over 2, or -1. Now think about what we just did on the front page. What does the slope of the secant line have to do with possibly finding some value of C? Okay, even look up here. We just calculated the slope of the secant line. That has to be parallel to some other line that is tangent at point C. Okay, well, how do we find the equation or the slope, not the equation, the slope of the tangent line? Well, we find the derivative, right? So let's take a look at that. If I have f of x is x cubed minus x squared minus 2x, then I'm saying that there is some C value, okay? Or actually, I'm gonna back that up. I'm just gonna put it as what is the overall derivative? And that's 3x squared minus 2x minus 2, okay? So what the mean value theorem is saying is that let's pull these two concepts together. This is the slope of our tangent line, okay? The slope of our tangent line has to be equivalent to the slope of the secant line at some point C. So we want to know C. Okay, so I'm going to say what is f prime of C? And that will have to be -1, which is equivalent to 3c squared minus 2c minus 2. Okay, so once again, what does that mean? This is the slope of my secant line, which must be equal to the slope of my tangent line because they're parallel. That's what the mean value theorem is saying. There is a C that exists. There is some point where the slope of the secant line is equivalent to the slope of the tangent line. Now find C. Okay, so luckily for us, we've all mastered our algebra. So I'm going to say that 0 is equal to 3c squared minus 2c minus 1. I believe this factors. And I'm going to end up with a +1 and a -1. So I'm getting that C is a -1/3 and C is a +1/3. Oh, nope, I just did that wrong. Let me back up. That is not the correct factors. That would not multiply back to what I had. C -1, right? So let me see, 3c squared minus 3c. Yep, there we go. And C is equal to +1. Okay. So what does this mean right now? Okay. Well, here's the issue. As much as I want both of these answers, can you have a tangent line at an endpoint? Remember, like a tangent line, the slope of a derivative, we'd have to be approximating one from both directions. So if I was to look at this function, because I think it's super good for us to take a look at this graph, okay? We know that -1, 0 is a point on there. 1, -2 is a point on there. Actually, even if I just come back and look at this, I've got an x-intercept at 0. I'm just trying to get some points for myself. Okay. All right. So we could graph this a little bit more if we needed to. But overall, I think we got something like this going on. Something along these lines. Okay. And I'm okay with you using a calculator if you want to check it out. Okay. Our secant line is connecting these 2 points. Here's my secant line. So I'm asking you where, at what value of C, do we have a tangent line that's parallel to the secant line? C = 1 doesn't make sense. How am I going to draw a tangent line over here? It would be the line itself. Okay, so going through 1, it's the line itself. I'm looking that there's got to be a line somewhere right along here. And so if we drew that in, if this is my tangent line, what we're finding out is that the x value of that point is at -1/3. Now, I'm not asking you to find the y value. It's just saying find all values of C if you read the directions. Okay, C is -1/3. Okay, so there is an application of the mean value theorem. Okay, so let's quickly go through the rest of these just so that we don't make this video too long. Okay, so example 2, explain why the mean value theorem does not apply on the function f of x equals the absolute value of x minus 3 on 0 to 6. Okay, so the first thing I'm going to want to do here is I want to graph this. So x minus 3, the absolute value. All right, I'm just remembering back to my parent functions here. We've got a graph that roughly is doing this. Okay, so why does it not apply on the interval of 0 to 6? So even coming out here one more. Okay, well, in order for mean value theorem to apply, certain conditions need to be met. So the first one is f of x continuous on the interval? So f of x is continuous. That's no problem. But is f of x differentiable? Okay, where do we have a problem with the limit of our instantaneous rate of change from both sides? And that's happening right around here. In order to be differentiable, remember, smooth and continuous, this sharp edge is causing a problem because the slope from the left of 3 and the slope of the right of 3, they're not equivalent. So where we have a problem is that f of x is not differentiable at x equals 3. Okay, and since x equals 3 is on the interval of 0 to 6, it's not going to work. Now, if this question had asked something about the mean value theorem or estimating a C value, and we changed the interval, then we would be okay. All right, but not with the way the interval is set up currently. All right, so last question. If f is differentiable on 3, 9, will the derivative equal 0 at some point on 3 to 9? Okay, now this problem's a little bit trickier. Okay, so first thing that I want to highlight is that they're telling us it's differentiable, which also means that this implies continuity. Okay, so if we just start from the beginning of does this problem satisfy the two conditions of differentiable and continuous? Yes, it does. Okay, so now we can keep going. All right, in order to get that the derivative has to equal 0, keep in mind of what this means, okay? We have a tangent line with a slope of 0. That is what's being given to us, okay? So if we know that we have a tangent line with a slope of 0, what this question is asking is, do you have a secant line with a slope of 0? So keep this in mind. If the derivative of f of x equals 0, then what they want to know is there a secant line where the slope will also be 0? Okay, so I'm thinking here, slope of secant line. Okay, well, in order for this equation to occur, we need this to happen. It's not so much about the denominator, but we need, whoops, 0 to be f of b minus f of a. Look at your table of values, okay? Where on the table of values could we get that the output of one point minus the output of another point is 0? So here's all of the outputs. How would we get that we would end up, how would we end up getting a 0? Okay, only if these two numbers are the same, right? So where on the graph do we have the same outputs? Here, we get an output of -4, and here. Is that on the interval of 3 to 9? First of all, yes, it is. So this is a good thing, okay? So this only occurs, or this can only occur at 3, -4 and 7, -4. So let's calculate this. Let's take a look, okay? So if we had f of 7, oops, I don't know what just happened there. F of 7 minus f of 3, okay, all over 7 minus 3. Okay, well, think about what that means. We've got -4 minus -4 over 4. We get 0 over 4. Okay, well, yeah, then that means that we have the slope of the tangent line is equal to 0, which is also then equal to the slope of the secant line. So what does this tell us? Because the question's just saying, will this occur? Okay, can this actually happen for us? Well, yes, this can happen by the mean value theorem, because let's think about the conditions that we know. F of x is differentiable and continuous. This is a really important part of what you state when you're writing a problem. Mean value theorem cannot hold unless we have differentiable and continuous, okay? Over the interval 3 to 9, okay? Since this is happening, there must exist, okay, or there exists a C where f prime of C is equal to f of b minus f of a all over b minus a, which equals 0. Okay? We're proving that somewhere over the interval of 3 to 9, we will have to get a derivative of 0. Okay? So because the secant line, think about the work that we're doing. We're saying because the secant line ends up with a derivative of 0, then there must be a tangent line with the same slope because they're parallel to each other. Okay? That's what mean value theorem is telling us. So we calculated the slope, proved that there is a slope of a secant line that is 0. And by the mean value theorem, then there must be a tangent line as well. Please don't get hung up on, hey, what is C? It didn't ask us for that. Okay, it just said, will there be some value of C? Okay, so everyone, that is the end of our lesson for today. Okay, you guys have some problem sets to work on for this section. So good luck, bring questions to class, and let us know if you need any help. All right, take care. Bye.